Okay, so what are we covering today? CNNs and ResNets, which are basically like kind of more old school stuff for image recognition, but a lot of the techniques will transfer to when we want to build up to bigger things like LLMs next week. The first thing we're covering is basically like neural networks from the ground up. So I hope that everyone is already familiar with like roughly what a neural network is. Basically, at a high level, it's just a bunch of matrix multiplications, one after the other, in like the very simplest case for the older school, what's called feed-forward networks, or multi-layer perceptrons, or MLPs. Basically, a map mul, some nonlinearity, a map mul, some nonlinearity, and you stack a bunch of layers deep. More bigger networks for image recognition are basically something similar to this, but use an extra layer, what's called a convolutional layer I'll talk about in a bit, for reasons that I'll talk about in a bit. But on a high level, basically we have a whole bunch of weights. The weights are trained somehow during gradient descent in whatever way makes the loss go down. So all we do is we specify our objective function with our data, do whatever makes classification better, do whatever makes loss go down. The optimizer will move locally in the direction that makes loss go down, and then afterwards we sort of discover after the fact the properties that the neural network has learned. So this video, if you're a bit fuzzy on ML basics, 3 Blue 1 Brown has an absolutely fantastic video on it. I recommend like watching this your own time if you've not seen it already. I think it's also in the prerequisite material. Okay, on a high level, PyTorch gives us this lovely little thing called a module, which allows us to find our own little blocks to build up neural networks. Each block contains, as far as you're concerned, 2 methods. The initialization method, which basically you'll define your parameters for the neural network, all the things that the optimizer is allowed to touch during training, and the forward pass for what the network actually does. So for a simple multi-layer perceptron, let's say it's just got like 2 weight matrices and like 1 hidden activation in the middle. You will define like your weight matrices here. You'll define like their size and their shape. We initialize them with a special little piece of code called NN parameter, which allows PyTorch to go, oh, okay, these are weights that I'm allowed to jiggle during training, and they're automatically registered for you, such that when you tell the optimizer, please optimize this model, it knows which things it's allowed to fiddle with and which things it's not. For example, we probably wouldn't want like the learning rate or the batch size or the physical size of the matrices to be things that the optimizer is allowed to like mess around with during training. These are hyperparameters that we choose ahead of time. But the numbers registered inside an NN parameter itself, these are the things that it's allowed to jiggle during training. And then during the forward pass, when you run through the network, this is the code that gets called when you actually call the model as if it's a function. And so you can say, like, run the first matrix, then do a ReLU, and then run the next matrix, and then spit out the output. So this defines like what the network actually does, how you use those weight matrices to do something. Hopefully everything pretty chill so far. Great. Okay, here's a high-level training loop of how we actually train the model. Broadly for training in general, it's always going to be something like this. For when we get to large language models and we train it to do next token prediction, this will change a little bit for like rather than classification. But broadly, the training loop always breaks down into these few steps. So basically, for the number of epochs, the number of times we want to run through the entire data set, we have a train loader from which we sample batches of data. In this case, we're going to be training an image classifier. So each batch of data is going to be a collection of pictures and a label for each picture. So each batch might be, let's say, 16 images from the MNIST data set, which is just 16 pictures of like numbers from 0 through 9. And the labels will literally be what number that corresponds to. So the image might be like a 24 by 24 black and white picture of the number 6, and the label will literally be the number 6. And the goal is we want to like twiddle the model such that it's better at labeling these images correctly. So the first thing that we do is we, presuming we're using a GPU, which we're going to be, is we physically move all the junk onto the GPU. For small training runs, if your network is very small and your images are quite large, this can often be like a dominant factor, just like shuffling garbage back and forth between the CPU and the GPU. Bandwidth and latency, both bandwidth and latency can be a constraint. So in general, you want to try and move the minimum amount of stuff back and forth. You want to do like 1 move data to the GPU and then 1 move back for whatever it is you want to get back from the GPU. So you'd like moving stuff back and forth can be like a real latency killer. So we move our stuff to the GPU. We then query the model. So I feed the images into the model, and the model spits out are what's called logits, which are essentially once you turn them into probability distributions with softmax, they're the model's guess at how likely it thinks this image is for each category. So for a single image, we'll get back a vector of 10 numbers that represents the model's confidence. This is the number 0, the model's confidence, this is the number 1, so on and so forth. Now in practice, feeding through images one at a time doesn't saturate the GPU. So in practice, we feed through like 10 images at a time, and we get 10 predictions all at once. Because to run a neural network, it's inherently a sequential process. You can't run layer 2 without running layer 1 beforehand. So to feed through a whole batch of images, we just run them all in parallel. And in general, all else equal, you want to make the batch as big as possible until the GPU is fully saturated. It's got no more little workers to do any work. So you'll find that as you make the batch size bigger and bigger, it doesn't actually run any slower until the GPU is like fully throttled, and then it starts being slower. So in general, we want to keep the GPU busy. We want to keep feeding it as much work as possible to keep him happy. So move chunk to the GPU, run it through the model, and then we compute the loss. So in this, we use a cross-entropy loss, which for the moment we will put aside what that is. Basically, it's some sort of measure between how good was your guess versus what the truth was. We have some sort of measure between these two. And the loss always has to be a single scalar value. If you have like multiple different things you care about, I don't know, suppose you've got like a taxi and you want to like get to your destination, you might care about multiple things. You might care about getting there as fast as possible and also getting there safely and also not consuming too much fuel on the way. This is like a multi-objective loss function. PyTorch can't deal with this. At the end of the day, there's going to be a single number, and you've got to make like this single number go down or up, and the optimizer does whatever it does to make that happen. So if you're optimizing for multiple things at once, this is like a whole different problem that PyTorch, at least in our framing, can't deal with. So feed stuff through, compute some measure of goodness, and then loss.backward. We have an entire day of content basically on like what this guy does later this week. Basically what this will do is it will, for every parameter in the network, it will compute what is the derivative of the loss with respect to this parameter, which gives me a gradient, a direction in which to bump this parameter up or down to make the loss locally go down. This is computed with what's called backpropagation, which is an efficient way for computing the derivatives of everything in the network. By the forward pass, you run forward through the network, and backpropagation, you run backwards through the network. So you compute the derivative of the loss with respect to the last parameters, and the derivative of the loss with respect to the second last parameters via the chain rule, and then you just you work all the way back through the network. So now what we've got is the gradient of the loss with respect to every parameter in the network. So if we have 1 million parameters, now we have 1 million little gradients. We ask the optimizer to do whatever it does to make the loss better given the gradients. So optimizer.step is like, you can use like lots of different optimizers. In the simplest case, using stochastic gradient descent, this will literally take each parameter and bump it a bit in the direction of whatever is downhill. For more complex optimizers like Atom or RMS prop, which is you'll see on, I think, day 3 or day 4, we have a whole day on that as well. You'll learn exactly what those optimizers do. But for the moment, this is a magic black box. Optimizer, please make loss better given the gradients. And the last thing that we do is we reset the gradients after each forward pass. So by default, PyTorch will just keep accumulating gradients in the background. If you do 2 forward passes, the gradients will be the sum of those 2. So you do a forward pass. When you do the forward pass, the gradients are computed. When you do a second forward pass, the gradients are added, and they'll just keep adding up. This is useful if your GPU is tiny and you want to emulate a really big batch size, but you don't have the VRAM for it. You can do like 2 forward passes on like a chunk of 32 images and another chunk of 32 images, and then do a step. And it's as if you did a step on a batch size of 64. So sometimes this is called like mini batches. But because we don't care about that, we're not doing that. After each optimizer step, we have to zero the gradients so that we're not using gradients from a previous forward pass. And that's it. That's like the entire training loop. So move stuff onto GPU, ask the model what it thinks, get a measure of how good it did, compute which direction is downhill, and let the optimizer do something to make the loss better. All training loops roughly look like this pattern. Does anyone want to ask me any questions about this? Okay, cool. Convolutional neural networks. building the convolution from scratch is a pretty tricky exercise. So this is like one of the bits of like bonus material for the day, is actually like writing the big nasty as-strided and einsums and all the nasty operations to do this. But basically the rough idea is images have locality. An MLP, multi-layer perceptron, when you feed it an image, well, it can't deal with an image, but it can deal with a vector. So you take the image, you flatten it to a vector, and then you do a big fat map mal. Now the problem is, if you take the image and you translate it slightly to an MLP, this is a wildly different input. MLPs have no sense of locality, whereas a convolutional neural network does. If you take the image and bump it slightly, and you wipe a filter or a kernel across the image, the output's going to be similar. And we want to abuse the fact that like images that are translated slightly are still kind of the same thing. A picture of a dog, if you bump it slightly, is still a picture of a dog. And we want to somehow encode this bias towards locality inside the model itself. And so we do this with what's called a convolution. How the convolution works is you have your input image, you have a kernel or a filter. You take that filter and you essentially treating this 3x3 matrix as if it was like a vector of length 9, and treating this 3x3 image as if it was a vector of length 9, you dot product the two things together. So this number times this number, plus this number to this number, all the way through, and then the sum gets stored here. We then put the filter on these chunk of numbers and do the same operations, store the result here, and then we rinse and repeat. This is equivalent to an MLP if you like snip a bunch of edges. Convolutions are a special case of MLP, except for the case that there's like way fewer weights to specify. The only weights are to specify here in the filter, whereas implicitly an MLP could have edges from every box in here to every box on the output. The fact that the convolution has fewer weights, it's constrained to something that must be local, allows the model to A, train faster, and B, generalize better. So even though an MLP can, like, technically speaking, express a larger class of functions, in practice it does worse, which is like somewhat surprising that the convolution is like smaller and faster to train and does better than the MLP. Like, in practice when you train it, you'll get like lower loss on the training set because the MLP will memorize, but the testing loss is like garbage, it's like super high, because it hasn't really learned, like, I don't know, what a dog looks like. So mostly for today, we just use the pre-built definition of two-dimensional convolution, but if you get to it in the exercises, you like write the whole thing from scratch, which is like a pretty gnarly operation. I think intermediate values are like 5 tensors, 6 tensors, big yucky einsums. It's like a pretty tricky exercise. And it turns out that if you train convolutions, early ones tend to pick up very low-level features like edges or circles or squares or something like that. And later, deeper in the model, they pick up more higher-level features. So like one of the earliest attempts at interpretability on models was for image models. And we found like wacky stuff like a Spider-Man neuron. And there's like a particular neuron in the model that seems to fire on like text related to spiders and drawings of Spider-Man and pictures of Spider-Man. And like lots of different image models seem to always have like a Donald Trump neuron that fires for like red hats and pictures of Trump. And this is like, I think, rather surprising that like models always seem to like pick up on like very human interpretable features very late in the model. So a lot of the early work on interp, Chris Olah has like a wonderful blog post where he details this. They find like car neurons that respond to like wheel neurons and window neurons and car body neurons, and if these three things fire, then the car body neuron fires, which I think is like quite neat. So a lot of the early mech-interp stuff before LLMs came from image models. Cool. Any questions about what I'm talking about so far? Hopefully everything's pretty straightforward. Yep.
What is the output array, or is it just like an intermediate state in the network?
Yeah, I would say like the input is just like an image grid of pixels. Intermediate value, I mean, it's like sort of harder to like give a useful meaning to this. If the filter that you dragged across it was something you've hard-coded for like detecting horizontal edges, then you could treat this as like the more brighter the pixel, the more horizontally the edges. And early on in the network, you can kind of see this, but later on it gets a bit harder to interpret. So shrug. Cool. Okay. Skip connections. So ideally, networks with more layers should be able to express strictly more stuff, because you could just have the later layers be the identity matrix and then it like doesn't do anything. However, in practice, training networks with really deep networks with lots of layers just does garbage. And the reason why is because when you stack a bunch of layers together, suppose each of them were to like, I don't know, bump up the gradients just a little bit, like let's say each layer multiplies the size of the gradient by let's say 1%. After you run it through 80 layers, the gradients are going to be huge, you make huge big leaps during optimization, training is terrible. Suppose the gradients shrink a little bit after each layer, then if the network's kind of short, then like no big deal, but the network's very deep, then like your gradients vanish to zero, you get stuck, you never learn. This is bad. We had trouble training deep networks for a very long time until someone had the bright idea of adding what's called a skip connection or a residual connection, where basically the output of each layer is whatever that layer does plus the input. So this thing is actually computing by default the identity. If you imagine when you initialize a neural network to random weights, by default it's doing, I don't know, some noisy garbage. So by default, the network is doing identity plus some noise. And it means that like if this thing like screws up the gradients really bad, they still have a path to go around the outside. Because if you differentiate this thing with respect to the part in the middle, the derivative is going to look like basically identity plus derivative of f, if you differentiate this thing. Which means when you do backpropagation, there's a component of the gradients due to the layer itself, and there's a component of the gradients that just get handed to you from the previous layer. So this means that like training is a lot more stable, gradients don't tend to like vanish, go to zero, or diverge, blow up to infinity. This makes training a lot more stable, it means we can train very deep networks. There's one other nice little benefit that I'll like briefly talk about, is that you essentially get an ensemble of models. Suppose you have, let's say, a two-layer neural network. This is like the only thing it can do. You do operation F, and then you do operation G, and then you get whatever the output is. If I add skip connections here, then essentially there's like 4 neural networks here. There's the skip both of them, there's the do F and skip G, there's the skip F and do G, and then there's the do F and do G. And the output that you get is like some kind of like weighted mixture of these 4 networks all together. And if you imagine you have like n layers, then you've kind of got an ensemble of 2 to the n different models of all the ways you could choose to run through or not run through a particular neural network. This is like one interpretation they give you in the paper while they sell you this is a good idea. I don't know how strongly I believe this, but in practice it like does pretty well. So an intuition was given to me, and so I give it to you. We'll come back a bit more to this when we get to transformers on the idea of the residual stream being the information pathway. But for the moment, think of it as a way for gradients to sneak around, such if a network is doing something stupid, a network later on will still get valuable training and training gradients with which to update. Cool. Any, yep?
How does skip connection protect against exploding gradients? I understand how it protects against vanishing gradients, but against exploding, I'm not sure. We still gonna get this big gradient, even if we like sum up the identity gradient and the gradient of the layer.
Yeah, so my short answer is I don't know. My slightly longer answer is my best educated guess would be I would imagine when the network is randomly initialized, each of these layers is probably going to poke the gradient in like a random direction, and so they probably kind of sort of cancel out. But my actual answer is like, I'm not sure. That's my best educated guess on the spot.
You can initialize them with a smaller set of weights in the first place because they're starting from the identity rather than starting from 0.
Oh, yeah, that's a better idea. Yeah, so if you have a really deep network and you don't want the gradients to explode, you could initialize them all really small, but now like your gradients are really small, learning's really bad. But here you've got like, by default, the network just wants to do that identity, and that's a much better place to start from than starting from 0. Because you start from 0, you spit out 0, you don't learn anything, you don't change anything.
Against vanishing gradients, no problem, but against exploding, I guess people just eclipse the gradients instead of doing
Yeah, in practice, you can do all sorts of tricks. During training, you just like snip the gradients if they're too big. Like there's lots of hacks you can do on top of this. Yeah. That's like the high-level short description. Yep.
I have a question about the like 4 different paths
Yes.
explanation. So it makes sense to me that this works empirically, but is it not the case that you could, like x plus fx could be represented by some other f prime x, which is also just the layers without the residual connection?
Like in practice, could this thing learn to just do f plus identity? Yeah, sure, right? You could just like take the weights and just add the identity matrix to it. Now it pretends to have a skip, but it's getting there is the hard part, right? Like after the network is done, I guess you could bake in the skip connection, but it's getting to a sensible matrix in the first place that's hard during training, and that's what the skip helps with.
So you're not actually using new combinations, the 4 combinations that you mentioned?
Oh, no, we don't actually run all 4 paths. I claim that like when you do a forward pass, this is like mathematically equivalent to running the 4 paths and aggregating them in some way, but we only do one forward pass. We don't run all the n paths, all the 2 to the n paths. Yeah.
I wanted to add on the instability discussion because exploding gradients is something, training instabilities can happen, but there's a lot of other tricks as well, such as normalization between the layers to like normalize the input such that this doesn't happen.
Yeah.
Yeah, there's much more, but I think it's good to know.
Yeah, we'll see that. I mean, we do batch norm. I think we do batch norm today for exactly this reason, and that you do it and it's super deep, and then gradients tend to explode anyway. So there's other tricks you do like batch norm and layer norm, and you have to have these if your network is super deep. So, but we'll skip that for now. Cool. I think that's basically all I wanted to talk about. So maybe a last few minutes for questions, and then we'll get started for today. Yeah.
Not really a question, but presumably one brand also has amazing videos on convolutions.
Yes, he does, and they're pretty great.